Ladies and gentlemen, we begin the afternoon session today with, I think, a well-anticipated event. This is the Fields Medal Lecture of Ngo Bao Chau. Chau, I hope, is not too tired. He spent a good part of the late morning signing reprints of his article, which I think are just off the press. It's the first I've ever heard of a mathematical book launch, but he did over 200 signatures, so I hope his fingers are not too tired. Chau was born in 1972 in Hanoi, Vietnam. He received his doctorate in 1997 under the direction of Gérard Lemma. He, in his short career, he has already won a significant number of impressive honors, in addition to the Fields Medal, which was conferred on him 2 days ago. He, in 2004, he received a Clay Mathematics Institute Research Award. He gave an invited 45-minute address at the ICM in Madrid in 2006. In 2006, he also received the Prix Sophie Germain de l'Académie des Sciences de Paris. And then, as we all saw, he was awarded the Fields Medal here in the morning opening ceremonies 3 days ago, excuse me. In his short career, Chau has written 14 generally quite long, deep and interesting papers, by and large all on the theme of geometrization of traditional methods in representation theory and automorphic forms. So let me present Ngło Bao Chau. His title is Endoscopy for Automorphic Forms.
It is a great honor to give a talk here in Hyderabad. I would like to thank Jim Arthur for his presentations. It's a real pleasure to be introduced by him. In my talk today, I'm going to try to give general pictures about the fields of automorphic representations, and on to the end, I say something about the proof of the fundamental lemma. But in the between, I will try to explain, to give an idea about what fundamental lemma is good for in a theory of automorphic representations. Okay. So I'm going to start with the end of the fabulous story of Fermat equations. That was a famous Wiles theorem on the conjecture Shimura-Tanya-Malvey. So we start with elliptic curve. Elliptic curve is the quotient of the complex plane by lattices. So it's an abelian group equipped with a structure of compact Riemann surface. So it's at the same time an algebraic curve. So it can be given by an equation of third degree, y squared equals x3 plus ax plus b, where a and b are parameters. So we say that E, the elliptic curve, is defined over Q, over the field of rational numbers, if the parameters A and B are rational numbers. So in that case, the Galois groups, the transformation of the algebraic closure Q bar, act on the finite group of L to the n torsion point of the elliptic curve for every prime number L and for every integer n. So this group of torsion groups can be easily described as L to the n of lambda mod lambda. But the action of the Galois group on this group is very interesting. So altogether, these actions form a system of two-dimensional analytic representation of the Galois groups. And this representation encodes almost all arithmetic information about the elliptic curves. For all but finitely many prime P, E can be reduced to an elliptic curve EP divided over FP. Reduce, that means you just reduce the equation modulo P where it's possible. So when the reduction is in elliptic curve, we say that the prime P is unramified with respect to E or respect to the representation rho. So for the finite field, we have the very basic transformation of the algebraic closure upon Frobenius element given by the formula you see on the screen. There is no way to leave the Frobenius to the Galois group of the rational numbers. However, for unramified P, rho E of Frobenius is well-defined conjugacy class in Gn2 of QL. So for unramified P, we do have a well-defined conjugacy class of the Frobenius. And the number of points in which value in Fp on the elliptic curve can be calculated by this very beautiful formula, 1 plus b minus trace of the conjugacy classes. So the number upon Fp is basically the number of solutions of the congruent equations, y squared equal x3 plus ax plus b. So the theorem of Y says that there exists a weight 2 modular forms, so F and Q plus A2 Q squared. So Q is the parameters. So this is the holomorphic modular forms, such that AP, the number AP appears as coefficient in this formal series for all unramified P. So all these number of solutions of congruent equation can be encoded in one unique analytic object that is weight 2 modular forms. So this is the theorem of Wiles for semi-stable elliptic curve and Wiles, Taylor, Wiles, and that was generalized by Broglie, Conrad, Diamond, Taylor for all elliptic curve over Q. Okay, this is a very typical example of more general Nonabelian reciprocity law between one side irreducible Galois representations and the other side Cuspidal automorphic form for GNL. So a modular form is generalized in the Cuspidal automorphic form for GNL. And this actually is a theorem for the so-called geometric function, geometric global fields, the field operational functions of a curve. So this is a great achievement of mathematics, the theorem of Laforgue, that who generalized Greenfeld works in two-dimensional case. So this is a case that the base fields is the field of operational functions on an algebraic curve defined over finite fields. For in the number theoretic case, for rational numbers, it's much more difficult. It's even much more difficult to state the law, the conjectural law, because they are automorphic forms that do not correspond to Galois representations. So to state it correctly is only a problem. And you know, even for Gn2, there are automorphic forms that are the mass form do not correspond in Galois representation. And historically, the automorphic forms are functional on Hermitian symmetric domain, so not related to GNN. So it is natural to consider automorphic forms on classical groups as well as GNN. So we have to shift the focus a little bit from GNN to on reductive groups. So at this place, Langlands introduced a kind of a simple but really formidable idea about the dual groups. Let me explain the dual group is. The construct is combinatorial. It looks quite artificial, but it's actually a very powerful idea. So I restrict myself to say split reductive groups. To a split reductive group, you can attach root datums, x that you see on the screen. Here, x is x check as dual Nonabelian groups. and phi checks are finite subset of X and X check. So this is the root, set of root, and this is set of co-roots. And the dual groups is a group defined by complex numbers. It's just defined by exchanging characters and co-characters, roots and co-roots. And that define a reductive group up to conjugacy. So that is the dual groups. So for example, G and N is dual with itself, S and N is dual with PG and N, SO2N is dual with SO2N, but that quite a funny equation as symplectic group is dual to the orthogonal groups. And this notion of dual group is basically related to the so-called Sakake equivalence. The classification, unramified representation of G of FV, FV being a non-optimal local fins. Those are classified by semi-simple conjugacy class in the dual groups. So at this point, let me just say that the local component of the automorphic representation are unramified almost at every prime. So that's why unramified representation as the first thing should be understood. So now let me recall the notion of briefly automorphic representations. So for every global fins, either arithmetic or geometrics, and for every absolute values, let them know FV, the completions with respect to that absolute values. And the range of Rn is just a product, basically a product of all the local fins. And you can say automorphic representation are just irreducible sub-representation of the group of G, which value in Rns, over the L2 of GA mod GF. So this is not, image to see, but in KGN2 is more or less the modular forms. And the chi are the central characters. So because pi is irreducible, it's more or less immediate that pi can be written as a complete tensor product of pi v being a representation of the log G of FV. FV is local fins. And we know that for almost on V, almost on prime, pi v is unramified, in the sense that pi v having a fixed vectors under the maximum compact. So it's very important to understand in which circumstances. If you pick pi v in some kind of random way, in which circumstances the tensor product is automorphic, that is a sub-representation of the L2. And Langlands gave a predictions based on not on the globe, on the Galois group, but some kind of local, very elaborated forms of the Galois groups. The group itself is hypothetical, it's not known to exist right now. So now let me state the Langlands reciprocity conjectures. So G is reductive group, assumed to be split. So so this LFV, it does the complicated form of the Galois groups. For local fins, this will be extension of the local V group by compact Lie groups. And the local reciprocity law stipulate that the admissible representation pi v of GFV are parametrized by homomorphisms, some kind of homomorphism from LFV to the dual groups. That should extend the non-parametrization for unramified representations, which are the static equivalence, is known. And for global fins, much more complicated. There should be an extension NF of the global V groups, given with homomorphism from the local NFV to NF. So, instead of NF is not known to exist as hypothetical groups. This is called the so-called Langlands hypothetical groups. And automorphic representation pi should be parametrized by homomorphism from NF to G hat. And local parameters, so pi equal tensor product of pi v, and pi v should be parametrized by phi v that are obtained just by restricting phi from LF to LFV. So the recipe is very simple, but the important fact and the unfortunate fact that NF is not known to exist. So this is important conjectures, but the basic ingredient, we do not know how to construct it. So this is a very serious problem. But there is a consequence of these conjectures, as the Langlands functoriality conjectures. So if we let rho homomorph from H hat to G hat, then for every automorphic representation of H, you should have a way to transfer to automorphic representation of G in such a way that at the unramified place, if PHV is parameterized by some conjugacy class, SV H hat, then the pi V is parameterized, is unramified and parameterized by the image of that class. So this can be seen as obvious consequence of the reciprocity law, but somehow it can also be seen much more primary than the reciprocity law, because these conjectures does not depend on the hypothetical group LF. So I think for many of us, this is considered the ultimate goal of the theory of automorphic representations. It's been very far-reaching goal. So the functoriality conjecture does not depend on the existence of the group LF, this Langlands group. But in fact, you can expect that the existence of LF should follow from the functorialities. So we should probably start with functoriality first, and then try to do reciprocity later. And also many deep conjectures in number theories are consequences of the functorialities, as you know, from Ramanujan conjecture, Satotet conjecture, and Artin conjecture, and so on. I don't have to try to stay on with them. So let me say about the known approaches to the functoriality conjectures. It's very partial. So first is kind of analytic method via the convert theorem. The convert theorem is a way to characterize certain representation to be automorphic by properties of L functions. And sometimes L functions have integral representation, like you can prove it. Then also the empiric method, and very respectable recent progress due to Taylor and collaborators on Satotet conjectures. So by empiric method, some kind of root form of functoriality can be proved, at least in KGN2. So this is really very important progress. So in my talk today, I will be more focused on the another approach called endoscopy theory. So establish special but important case of functorialities by the way of the stabilized trace formula. So let me start to say some word about this mystery world of endoscopy. So let's start with the case of S72R. What are the basic phenomena of endoscopy? It's very well known that when you restrict this discrete series representation with Gn2R to Sn2R, we got a reducible representation. Sometimes have 2 components, and they have 4 components. And the constituent of the restriction should have all same parameters. So if you start with the representations with the parameter from LR to Gn2, then the parameter and the restriction should just be given by the compositions. So all the constituents should have the same parameters. That means that the parameter is not 1-1 in the case SL2R. There might be more than one representation having the same parameters. So they are concept belong to the same packet of representations. And there's some kind of dual phenomena in the group SL2R. If you look at the rotation of the plane of angle theta and the angle minus theta, so they are both in the SL2R They are not conjugate in SN2R, but they are conjugate either in GN2R or SL2C. And they are stably conjugate. That is, so these two phenomena of packet of representation and stable conjugacies are dual one to each other. So let me formalize more notion of local packet. So local packet is finite set of representations of GFV parameterized by a given homomorphism phi 5V. So it's just some very formal definition because I don't know how to parameterize for the first place. But we are very close. So if you are given phi V, define S phi V be the centralizer of phi V. So all element of G hat that commute with the image of phi V. And we didn't know SO phi V is the connected component of this group of commutators groups, and Z of G hat is the center of G hat. And look at this quotient. So this is basically a finite group. It's usually very small, but it's non-trivial in general. And it's expected that there's natural bijection between the packet and the set irreducible representation of this finite group. And the global packet is just is by definition just the product of all the local packet. And the question I want to ask you, which member of this product is automorphic, that occur in the automorphic spectrum, and what is the multiplicities? And so if you are given a global parameters phi from L and F, this, conjectural group to G hat, Kottwitz define a way to have this another global finite group together with more from the local finite group to these global finite groups. And he considered a very nice formula for the multiplicities. So here pi v's are local component of a member of this packet, and you just pair look pi v's as characters of this S phi v, pair with each element of epsilon, epsilon v is epsilon actually, and make a sum. So this should give the multiplicity of the representations. So that comes to the endoscopic ideas. So that comes from Langlands' idea is that the packet and multiplicity can be explained by a special case of functoriality principles between G and certain smaller groups called endoscopic groups. So for real groups, Schoenstatt proved remarkable identity between sum of characters of representations between endoscopic group H and G, and that gave real evidence for the endoscopic program somehow. And Langlands suggests a more whole program to establish the endoscopic functorialities by the way of stabilizing trace formula that I'm going to explain a little bit later. So let me say a word about what the different endoscopic group, which is a little bit technical. So let S be a semi-simple element in G hat, and assume that the centralizer of S has the same semi-simple rank as G. And I could H have the neutron component of that centralizers. And the dual group of H hat is shown endoscopic groups. So I start for simple G to be G split, but in general, endoscopic group of split group may not be split, maybe even quasi split. But let me pass these details. So one of the remarkable examples, the SO2N is endoscopic group SP2N. So these two groups has this SO2 is not a subgroup SP2N. Some more familiar example, but it's very important, is UN1 times UN2 is an endoscopic group of UN as long as N is equal to N1 plus N2. So there's there are slightly more general setting that the twist endoscopic groups that I'm not going to define, but that include a very important case of the standard representation of classical groups. So this very similar to this, but more complicated. Right? I don't know going to define, but like SO2N, 2GN, 2N, SP2N, 2GN, 2N plus 1, SO2N plus 1, 2GN, 2N. So that is a very basic case of the twist endoscopy. And twist endoscopy also includes the very important case of base chain that was very important in number theory. Just mentioned that Y start with a case of acting conjecture that was proved by using base change. So via the way of stable trace formula and the twist trace formula, Arthur proved the functional realities of the endoscopic and twist endoscopic cases. And he obtained a classification automorphic representation of classical groups in terms of cuspidal automorphic representation of GN land instead of these hypothetical groups. And he also proved multiplicity formula that depend on more combinatorial data instead of the Kottwitz formula using the group LF. So the pictures for classical group is almost complete, except the fact that we do not have LF, but we have to start with the as basic data the cuspidal automorphic representation of GN land instead of LF. So there is also another very important application of endoscopy. It's called the construction of Galois representation attached to self-dual automorphic representations. So let F be a complex multiplication fin that is totally imaginary quadratic extension of a totally real number fins. And in that way, in that case, the complex conjugation define an involution on F, well-defined involution on F. And a representation pi of GN land of AF is looking at the pi that has conjugate self-dual, given by this formula. So pi dual is isomorphic to pi composed with complex conjugations. And that the component infinite have the same infinitesimal characters as some algebraic representations satisfy some regularity conditions. And then now we know there exists a continuous representation of the Galois groups, so that for every pi p, the local component of the corresponding representation of local Galois groups correspond to local component of pi v by the correspondence, local correspondence was established by Harris, Taylor, and Enyart. And this concern is based on the analytic cohomology of Shimura variety attached to unitary groups. And following a general study that was proposed a long time ago by Langlands and Kottwitz. And there are many people that have contributed to this formidable theorem, which I mentioned, some of them Golden Harris, Taylor, Yoshida, Labeste, Morin, and Shin. Okay. So now let me go to the next part of my talk. I explain you the very basic thing about trace formula and local harmonic analysis of the trace formula. So the trace formula is a formula of this form. On the left-hand side, a trace, and on the right-hand side, we have operant triangles. So trace P are trace or discrete automorphic representation of pi, and O gammas are global operant triangles attached to elliptic conjugacy class gamma of the group G. F is global fins. And there is a hidden part attached to the continuous spectrum, and as well as a contribution of hyperbolic conjugacy classes. And the test function F is a function of the adherence groups. Usually the form of tensor product of FV, where FV is smooth function is compact support on G of FV. And for almost on V, FV is characteristic function of the maximum compact. That is very important. That is why on the story is going to follow, the characteristic function of G of OV is play a prominent role because that is the function we check almost everywhere. So let me define more formally the stable conjugacy class, at least for the special case of strong irregular element. That is the element that set up the central ladder is a torus. And they are said to be stably conjugate if they are conjugate in G of F bar. The F bar is the algebraic closure of F. In general, the decision might be more complicated. And this is actually very geometric notions that gamma and gamma prime are stably conjugate if and only if they have same image in T mod W. So T mod W is the space, the spectrum of the ring of invariant function on G. Here T is the maximum torus and W is the Y groups. So if they have same image by the on-invariant functions, then they are stably conjugate. So stably conjugacy is geometric notions. And there may be more than one conjugacy class within a stably conjugacy class. Usually it's infinitely many of them. But they are parameterized by a subset, A gamma, of the H1 of the centralizers. So H1 of centralizer is basically the responsible for the stably conjugacy class, and there is a subset that parameterizes on the conjugacy class. And it happened that when F is local non-Archimedean fields, A gamma is a finite abelian group. It's a subgroup of H1, which is self-finite abelian groups. And let me introduce the stable orbital integral. So stable orbital integral is just the sum of all orbital integral in the same stable conjugacy classes. And because the set A gamma that parameterizes conjugacy class within stable conjugacy class is a finite abelian groups, you can form other linear combinations using characters of that finite abelian groups. So when kappa is a character, such characters, we form these linear combinations that are called kappa orbital integrals. And we say stable distribution is a distribution in the closure, with closure of the on finite combination of stable orbital integrals. And this is very important point to notice that trace formula is not a stable distributions because there is local versus global obstruction in Galois cohomologies. So that is when you pick gamma, a strongly regular element, and for every place you just train randomly to gamma V, to gamma to gamma pi V. Some elements that are stably conjugate to gamma V but not conjugate. And if you do that, there might not be gamma prime, global gamma pi, so that gamma pi is conjugate to gamma pi V. There are obstruction, Galois obstruction. That is why the trace formula is not a stable distributions. And the stabilized trace formula is basically you want to write the trace formula as a kind of overstable term. You need to work a little bit to see what is overstable term, but you can write stable term. And then you have to put error term that compensate the instability of trace formula. And obviously by a Fourier transform on A gamma, the error terms can be expressed in terms of kappa orbital integrals. So I said it very shortly, but it's a very complicated process. And the main purpose of the stabilizations is to compare the error terms that are made of kappa orbital integrals with the stable terms in the trace formula of the endoscopic groups. So the points can be reduced to a comparison between kappa orbital integral on G with stable orbital integrals on the endoscopic group H. So I said it very quickly, but obviously there is a huge amount of work to reduce to a local problem on the orbital integrals because the structure of trace formula is very complicated. So now I am on the point to state the local conjecture about operant triangles, in particular the fundamental lemma. So by using the Tate-Nakayama dualities in Galois cohomology, kappa, that is the characters of the obstruction of the group A gamma, can be thought as the semi-simple conjugacy class of G hat, more or less. I mean, there's more complicated than that, but let's just say it like this way to make it simple. And when you have a semi-simple conjugacy class, you can form the centralizer and the connected centralizers. That is a dual of the relevant endoscopic group corresponding to this kappa. So that the endoscopic group is related to the kappa, the characters. So though in general this H is not a subgroup of G, its dual is a subgroup of G dual, but the group itself is not a subgroup of G, there is a canonical way of transferring stable conjugacy class from H to G. I just draw by gamma H to gamma to the reason is basically that G and H share a maximum torus, and there is inclusion of the Weil group W, so that, as we know, that stable conjugacy class are basically classified by T mod W. So as long as we have the same T and WH is subgroup W, there is a way, a canonical way to transfer stably conjugacy classes. So the transfer conjectures is whenever we have a function f, smooth function compact support on G, there exists a smooth and compact function fh such that the kappa operant triangles is equal to the stable operant integral on H with respect to gamma and gamma H, gamma being the transfer of gamma H. And there are factors, very complicated factors, but the point is these factors depend only on gamma and gamma H and certainly not on F and FH. And the fundamental lemma is that these identities holds for very particular function. F is characteristic from the maximum compact, and FH is characteristic from the maximum compact for H at the unramified place of V. So when we want to use the trace formula to establish endoscopic case of the functional realities, you need both conjectures. At finitely many places, we have to play with arbitrary functions. But for all the other places, infinitely many one, we just have to put this particular function. So we should have two kinds of identities. The fundamental lemma for all but finitely many V, and the transfer conjecture for the finitely many remaining places. So these two conjectures remain for very long times, but now they are unproved. So let me repeat that Schoenstatt proved that the transfer in the case of real groups, that gives first solid evidence for those conjectures. And there are many particular cases that have been worked out by Labesse and Langlands SL2, Rogowski in U3, Kottwitz SL3, before Kasdan and Vansberg solved the case SLN, SP4 was written by Haynes, Schneider, and Weishauer. And one of the milestones of this story is the proof of Vansberg, who proved that basically transfer conjectures follow from the fundamental lemma. So the first conjecture follows from the second one. And there is another remarkable statement that were proved by Vansberg and Kluckers, Haynes, and Lohse by quite different methods, that the periodic case of the fundamental lemma is equivalent to the case fundamental lemma for formal series case, which is more accessible by using algebraic geometries. So basically, we are reduced ourselves to the fundamental lemma for the low confines of formal series. And now you can have more chance to use geometries. And the first step that was done by, not related to fundamental lemma, but Kasdan and Lustig introduced on alpha Springer fibers. That is basically a geometric incarnation of the local orbital integral. Somehow the motif of those alpha Springer fibers correspond to orbital integrals. And Kottwitz formulated the geometric fundamental lemma using the Alpha-Springer fibers and introduced the method of using equivalent cohomologies. And they proved actually that it's called undammified case of fundamental lemma, and it's a fairly particular case. It can be proved by equivalent cohomology if you know some continuity conjecture of the Alpha-Springer fibers, but which is not known. And also Lomong proved also that the fundamental lemma for UN would also follow from the purity conjectures. So at that time I was trying to prove the purity conjectures, but somehow I got a chance. I was trying to prove it using Hitchin fibrations, but then I realized that actually you cannot prove it, the purity conjecture with Hitchin fibration, but Hitchin fibration is really connected to the trace formula of Lie algebras. And so that's in the beginning of the global geometric method. And then Lomong and myself proved the fundamental lemma for unitary groups. So using the Hitchin fibrations and using the Lomong method in the unitary groups. And then in this work we use the equivalent cohomologies as in the Kottwitz papers. But I realized later that equivalent cohomology cannot be used in a genuine case simply because there's no more torus in genuine case, so you cannot use equivalent cohomologies. But there is another way to get around that. And let me mention that Lomong and Shouldwag also proved the weighted fundamental lemma, even twisted weighted fundamental lemma, that were necessary to stabilize the whole trace formula and all the arithmetic application that I mentioned earlier. Okay, so now let me go to say some word about the proof of the fundamental lemma. So the very important ingredient, the Hitchin systems. So we have a moduli space band G of stable principal G bundles of a smooth projective curve of genus larger than 2. So here G is any reductive groups and X is a compactly bound surfaces. So this was used in Hitchin studying some partial differential equation coming from physics that he called the moduli space fixed bundles. I don't really know why. So he looked at the band G, so the cotangent space of band G. So as cotangent space, this algebra, this varieties is equipped with symplectic structures. And Hitchin pointed out that it actually is algebraic complete integrable systems. So more precisely, he can define many functions on F that are Poisson commutings. So that we have a map F from M to A. A is basically a vector space of half the dimension of M. Dim of M is twice the dimension of A. And the Zurich fibers of F is Nonabelian varieties whose tangent space is isotropic with respect to the symplectic structures. So that is called algebraic complete integrable systems. And because of that the tangent space is isotropic with respect to the symplectic forms, there is a Hamiltonian flows who act as vector field on the fiber of F. So here the picture is fairly understood on the genetic fibers of F. They're just torus, but they're very singular fibers that are not well understood. That is actually what we want to understand. The singular fibers of Hitchin system is related to the orbital integrals. So it happened that in Hitchin papers, X is a curve defined of complex numbers, but all these definitions just can be used in any fins, in particular finite fins.
And in the finite fin case, the number of points of M is coefficient in the finite fins had the form of the trace formula for Lie algebras. So it can be as the sum of global orbital terms for Lie algebras. So this is very formal because M here is I consider as a stack, as number of points is not finite, it's infinite numbers. But if you write it in kind of formal way, we get to the formal trace formula. It's not convergent. So, but that is actually the very important clue that the Hitchin fibrations is more or less the same thing as trace formula for Lie algebras. And moreover, the number of points along the fiber of F can be expressed in terms of orbital integrons. The sum of orbital integrons in the same stable conjugacy class. So it's exactly what we want. And the next clue is that we realize that the Hamiltonian action of the vector fins can be naturally integrated into notion of group scheme. So in the different geometric pictures, there is some kind of local actions, but in the particular the Hitchin systems, there is algebraic actions, not a one group, but a group scheme, so the group depending on parameters, whose the tangent action is a Hamiltonian actions. And when you have group scheme, there's a group of connected component depending on parameters. And it happens that the whole endoscopy theory, at least in this Lie algebra case, can be translated entirely using the action of this group scheme. So we can translate the whole endoscopy theory of automorphic trace formula in terms of the in geometric terms using this group scheme. And doing that, you can, the whole fundamental lemma, for the fundamental lemma, or the global form of the fundamental lemma, can be formulated by some kind of properties on the direct image of F. So F is a map from M to A. So by the Lin theorem, we know that this is the pure complex periodic sheaf. So as a pure complex, we know it is geometric semi-simple, direct sum of simple perverse sheaves, shift the simple perverse sheaves, and the main geometric result is actually a description of the support of simple perverse sheaf that occurs as the factors of this complex image. So that's how following the theory of perverse sheaf that was invented by Goretzky Macpherson. So basically, you want to understand the singular fibers of Hitchin map from the genetic fibers. So genetic fibers are tori, abelian varieties that we understand. And we want to understand the singular fibers as well. If we know this geometric result about the support of simple constituent, we know that basically this complex is completely determined by its genetic locus, a linear stable part. So that you can control geometric, how you can control the orbital integrons, and that is how the fundamental lemma follows. I think I can stop here. Thank you.